Hello, welcome to this DevNation Live. My name is Rafael, and today our guest is Marius, and he will be talking about Kafka Streams for event-driven microservices. Please post your questions as you think of them, and we'll try to address them in real time. Some questions will be held for Marius at the end. So Marius, it's to you now.
Hey, Rafael. Can you hear me? Hello?
Yeah, Marius, we can hear you.
Fantastic. Thank you very much for the introduction, and I'm happy to be here and talk a little bit about Kafka Streams and event-driven microservices. So let me start by sharing my screen, and let's go with the presentation. First, I'm going to talk a little bit about what Kafka, like the features of Kafka Streams and how they help event-driven microservices. And then we're going to talk a little bit about how to run Kafka Streams applications on Kubernetes and OpenShift, and we're going to see a quick demo about how that works. As Rafael said, please feel free to ask questions. We're here with Rafael and one other colleague of ours from the Streamsy team, Paulo Paquierno. He's also going to be able to answer some of your questions as we go along if you have questions about Kafka. And we're going to save some questions for the end. So first about me, my name is Marius Bogovici. I'm a principal specialist solution architect at Red Hat. I specialize in integration, messaging, and data streaming. I'm an open source contributor since 2008. And I've been kind of very active in the Spring community ever since, in particular, and also in the JBoss community as well. So I take a deep interest in event-driven microservices and in Kafka, and I'm happy to share some thoughts here with you. First, the first question that we're going to try to answer is, event-driven microservices are a big topic. We're not going to go and exhaust all of them to really exhaust it today. It's worth a talk on its own, but we can take a look at a few points that sort of help us understand where Kafka Streams come into play and what specific problems does it solve for event-driven microservices. So why do we build event-driven microservices in the first place? Well, event-driven architecture in general helps us reduce friction. So it really helps us build robust and resilient distributed architectures. And if you kind of think of microservices as distributed solutions, then the relationship becomes apparent. It helps us from a development process standpoint because, generally speaking, event-driven architectures are very composable, and that encourages agility and experimentation. And from a business standpoint, modeling systems with events is a very natural choice because the world around us itself is really event-driven. So in that context, in the specific context of microservices, event-driven architecture helps solving problems such as state propagation. And this is where we have solutions as change data capture for streaming changes from a database, event sourcing for propagating state between different systems, CQRS for separating the read and write operations and allowing to optimize the different types of stores across a microservice fleet. So those are, let's say, this is where event-driven architecture mostly works as a technical solution for problems that are created by the distributed nature of these types of architecture. But there's also event-driven, there is also domain-driven design. There's also event-driven microservices fit very well because they allow us to model the world by creating events as first-class citizens, as a central part of your domain, right? So In both these cases, there are a number of challenges. One of the things that's kind of known about microservices is that coordinating state is hard. Like one of the basic tenets of microservice architectures is that it is composed of a set of applications. Each one manages its own state, and these applications interact with each other. Right? They can do that in a request-reply fashion, like synchronously, ensuring that a state, for example, a change, is propagated across an entire set of components. And that is hard because it really requires, like, it works under the assumption that nothing will ever fail. It works under the assumption that all applications are available. So event-driven architecture in this case allows to decouple these interactions and allows to decouple the change state, the state change, as I said, and essentially allows us to avoid doing things like distributed transactions. So that's kind of, this is solves, this is how event-driven architecture, for example, solves this state coordination problems. At the same time, if you look at the way these types of applications work, you end up with these pipelines of applications interacting with message brokers, interacting with databases simultaneously, processing inbound and outbound events, and essentially being coordinated and being grouped together into these large complex graphs. And that creates some challenges of its own. For example, a microservice has not only to, for example, to manage its own state, but it also has to do that in coordination with its communication with the broker. It also has to do that by making sure that all the events, for example, that all the inbound events have been acknowledged in conjunction with the state changes that it has been made, and also it has emitted all the events that are required. So, in a way, while this type of architecture is pretty common, there are solutions for this, but they add another level of complexity to the problem. So essentially, this is where Kafka Streams comes into play and essentially builds on top of Kafka as a distributed messaging system. So if you're not familiar with Kafka, I'm just going to do a very quick overview. And 2 weeks from now, at the next DevNation live events, one of our colleagues, Jakob Schultz, will present we'll talk more in more detail about Kafka and what we do with Kafka at Red Hat. But in summary, Kafka acts as a distributed messaging system based on a distributed log approach. So essentially, it adds more advanced distributed publish subscribe capabilities that mediate the interaction between a producer and consumer applications. As we saw in the diagram before, a lot of these event-driven microservices require to both coordinate events, require to do processing, and they're both emitters and consumers of events. They need to do that in coordination with their state management. So Kafka Streams comes in and proposes a solution where a client library is essentially embedded into the application itself. It comes as an alternative to, let's say, to stream processing engines that sort of require their own platform, and it actually allows you to embed stream processing features into regular job applications. The big change and the big advantage in the case of event-driven microservices is the approach that it takes to managing events and state. Everything is done using Kafka to Kafka semantics. So because it essentially works with a single component, with a single just because it essentially interacts just with Kafka. It allows to do this event state coordination. It allows performing like the stateful processing support that the types of applications that event-driven microservices require. And it also allows to implement more advanced patterns, such as transactions and exactly once interactions. Again, the approach here is that instead of creating topologies as part of instead of creating sophisticated topologies that are deployed on a separate platform, by embedding the library into the application itself, these topologies can be created out of independent applications as microservices. It comes with its own high-level functional DSLs. So essentially, every it maps on it maps over a set of inbound and outbound topics. And it allows to describe transformations as data flow from a topic to another. So it is a functional DSL, which basically describes the transformations of the data streams as they occur, and also allows more complex operations like grouping, counting, or in the case of tables, for example, operations such as joins. It also contains primitives for time windows, which allows to perform windowed-based aggregations. The main abstractions essentially reflect this topic-centric nature of Kafka Streams. So one of the abstractions is the K-stream, which is essentially the flowing stream of data. And essentially, it maps one-to-one to a topic. The other abstraction is the table abstraction, which takes the ordered and durable nature of topics and applies a changelog semantic to it. So essentially, as you know, a Kafka record essentially has a key and a value. This K-table abstraction will read a stream of data, for example, a topic, and will apply these changes into an internal key value map. So its view of the world is essentially as a key value map that reads the changes, that reads the records of a topic and applies them as updates on the map itself based on the record key. This table comes with its own set of complex operations, joins and aggregations. So this allows to create, for example, complex operations such as creating materialized views over ever-changing data streams. And one of the fundamental ideas in Kafka Streams is the stream-table duality. So given any stream, we can construct a table from it, understanding that the stream contains changes that are applied against the key. On the other hand, we can stream out the changes to a table as a stream of updates. So these operations, let's say, interplay between streams that contain the events that are flowing into the application and outside the application, and the tables that contain the materialized state the application observes are actually critical for understanding how Kafka Streams works. And of course, as I said, aggregate operations usually need a finite time window, and Kafka Streams essentially contains sophisticated time windowing primitives for describing how the aggregate operations take place. For example, calculating the average of a given of a value, for example, over the last second, calculating the average of a given value over a sliding time window, for example, the last 5 seconds updated every 2 seconds, and so on and so forth. So these are key for building these are key for building Kafka. These abstractions are key for building Kafka Streams applications, and they are reflected in the high level in the functional DSO. And we will see later on one example of such an application, actually, this word count application at work. The other challenge that happens with these like sophisticated distributed topologies, besides managing the event handling and state together and cohesively, is because these applications are like, because this model encourages grouping together functionality into distinct applications, we can end up in, this is kind of a design pattern of we can end up with complex topologies where applications are like, we're not only with a large number of applications, but actually we have requirements of scaling. So running this type of solution on your own makes for a very, very complicated approach. This is where Kubernetes and OpenShift, which is actually the enterprise Kubernetes platform, help by managing applications, by providing the resilience and reliability that applications run, by making sure that applications are restarted in case of failure. Also, it provides inbuilt resource management. So scaling, so creating new instances and scaling the number of instances of a given node, for example. That's what the platform provides. It provides monitoring and failover, right? And as I said, more advanced features in OpenShift are, for example, routing and load balancing, rolling like continuous integration capabilities. And these are critical for removing the complexity of running the topology from the application developer and handing it over to the platform. And again, this kind of mindset, the idea that these complex topologies are not only restricted to applications, but they actually apply to the Kafka clusters themselves, which are fairly complex distributed systems. So it follows that we can run and we can think of running our entire solution on top of Kubernetes. So what are the ingredients for that? First, how do we run Kafka on Kubernetes? We have, like at Red Hat, we have like our colleagues from the Streamsy team. We develop an open source project called Streamsy, and which is focused on running Apache Kafka and Kubernetes on OpenShift. As a solution is part of so Streamsy is, let's say, the upstream component. It's also available as a product, part of Red Hat NQ. And its goal is to essentially ensure the management of both clusters and like both Kafka clusters and topics, and kind of take away from the complexity of running these individually. The idea is that you can, for example, containerize your Kafka brokers. You can containerize your Zookeeper instances, and running them on their own and coordinating them. But Streamsy takes a different approach. It basically takes the operator. It uses the operator pattern to oversee a set of configurations that and declaratively update the state of the cluster. Install new brokers as necessary, start Zookeeper nodes, or size the cluster as necessary. You will not operate the brokers yourself. You will actually update the declarative configuration, and it's the responsibility of the cluster controller to manage that configuration for you. And of course, the same logic applies to controllers. So the configuration of the the configuration of like your topic configurations, instead of kind of going and opening the administrative console and administrating topics directly into Kafka, you will declaratively install like resources. You will create dynamically, you will create custom resources in OpenShift and in Kubernetes. And the topic controller will be the one that will take control and create these topics for you. Conversely, it will make those available as Kubernetes native resources. So essentially, the management of your Kafka cluster is reduced to managing your OpenShift cluster, right? So in this topology, essentially, the topology of running Kafka Streams applications in Kubernetes consists of containerized Kafka Streams applications that they're deployed using various mechanisms like source to image, for example, which is one feature that OpenShift supports for creating image streams and deploying these applications. That interact with a Kafka cluster provisioned on OpenShift as well. Everything essentially runs on the platform. Everything is managed automatically, and the responsibility of the user essentially is reduced to managing the resources that that control the size and the topics in the Kafka cluster, and deploying applications as individual as containerized apps. Both the events and the changelog in the applications themselves are essentially coordinated with the Kafka cluster using the Kafka Streams API. So let me walk you through a quick example of Kafka Streams running on OpenShift. So I have installed in my OpenShift web console, I already have installed Streamsy. I have the operators running, and as you can see, I have my Kafka cluster already installed in my current project. So what I will do next, I have 3 different applications that will interact with this cluster to create, let's say, a data stream. The first one is an application that will produce messages that the Kafka Streams application will process. It is a RESTful endpoint written using CAML that will output, like, every line submitted, every line posted to the service to this Streams plaintext input topic. Then my Kafka Streams application will take this data from this topic and will apply a series of transformations. So let's take a quick look at how the application works. First, it will transform this by splitting this into separate words. Then it will group. It will also convert these words to lowercase, so that when we're counting words, we're actually not affected by the case of the word. Then it will apply a group-wide transformation, and then it will count the elements of the different groups. Now, as you notice, the result of this, this is essentially a continuous transformation. So with a certain frequency, which is controlled by this commit interval configuration, we will output and stream the changes in this table. So essentially, we will stream what changed since the latest commit, as a pair of words and word counts. That pair of words and word counts is actually received by another application which is this, which is another Camel application in this case, which reads it from the output topic of the Kafka Streams application. So essentially, we will log the messages that we receive, and we will also retain them in an internal map so we can display them using a RESTful endpoint. So let's start first by deploying these applications. I'm going to deploy this, I'm going to deploy the different applications using the Fabricate, the Maven Fabricate plugin. So the Maven Fabricate plugin essentially takes the Uber jar created. Let's go through one of these examples. It takes the Uber jar created by the Spring Boot Maven plugin in this case, and it sets up an image stream in OpenShift that builds the container image. It also will set up a running application and a route. So we're going to do this for all the three components of the application. We will wait a little bit once as the image streams are set up and the applications are started. As you see, the images and the builds start being created. And this is quite a powerful mechanism for creating out of your Maven project a Dockerized image for your application by delegating the creation of these images and the process of containerization and installing those images as part of the internal Docker repository to OpenShift. Now, all my builds are complete, so I should see the three applications starting, and they do. They all started. Let's take a quick look at the Kafka Streams application. I want to look at the pod. It just starts. If you take a look at for example, at this application, the configuration option here, and I'm using Spring Boot and the Spring Kafka support to actually kind of push the environment variables and config map values into the application itself. It refers to this URL. This is the URL of my Kafka cluster. This is the bootstrap URL of the cluster, my cluster, managed by Streamsy. So as you see, all the addresses are internal and everything is contained into this project. So the applications are now active. As I say, let's take a quick look at the Kafka Streams application. I can see that the Kafka Streams process has started by this current active tasks. These are the tasks that manage the processing of the data from the inbound topic to the outbound topic. And let's start monitoring the demo word count REST application. So as you see, there is a lot of stuff being logged right now. This is because this is the current state of the topic that it monitors, which I remind you is streams word count output. Of course, we can also check the current values in the map. So I can just do a curl, and I can see that like it has counted the number of words. This is basically the result of trials that I made before we started this presentation. So let's start posting some data, right? And let me put this separate. As I'm posting this data to the inbound microservice, I can see a sequence of the updates being sent, which means that the Kafka Streams application has counted the words, the table has been updated, and the downstream service from that has received these values. And of course, I can go and now check the new set of values, and I can see the new words basically being, like the counts for DevNation, for example, being incremented from 3 to 4. And I can try a different value just to try it again. And of course, I can see new words basically coming in, like again, and I see the value for DevNation, for example, being updated to 5, which is again the result of the update into the internal table of Kafka Stream, of the Kafka Streams application. And of course, I can see a set of updates coming in here, which contain like the new counts for the new added words. So I'm going to stop now, and this was the demo, and I'm going to turn it over to Rafael and asking if there are any questions.
A couple of questions that you might be able to answer. We are a little bit over the time, but I think you can get some of them in the chat box. I helped you by sorting them, so please feel free to answer.
Perfect. Give me a second. I'm having some trouble getting to the chat box. Maybe you can read them to me.
Yeah, I can read to you. So one question: do you suggest Istio in the mix to meet application resilience requirements?
I think Istio. So Istio serves a different purpose here. First and foremost, Istio right now, so what we're describing is a process through which applications interact with each other through Kafka. Istio is kind of, right now, Istio is based on a request-reply pattern and mostly handles HTTP calls. There is a project going on, and there is a desire to extend Istio to support Kafka. In this case, it wouldn't necessarily add the resiliency, because the resiliency of the interaction right now is handled by the resiliency of the Kafka broker and the Kafka cluster itself. But it would help with observability and discoverability and security, for example, by managing the features such as mutual TLS at the microservice level. So to summarize the question, I wouldn't necessarily say that Istio would add much for resiliency, but it would help with other aspects once that integration is available.
Okay, and do you have any throughput comparison?
I assume that this is referring to the throughput of Kafka. So, and maybe, I don't know, maybe this would warrant a clarifying question. I think the throughput, like Kafka Streams itself, is natively based on Kafka producers and consumers. So the performance, let's say, of the system is comparable. There are some, for example, documented like for features, advanced features such as transactions, for example, or exactly once processing, that might decrease the throughput because of the additional steps that are taken to ensure those features. But generally speaking, I think they're within comparable levels. If the question is about comparison within between Kafka and other systems, then surely there is an entire literature about that. So
okay, perfect. So we have more questions.
To share some of them.
Yeah, since we are out of time, yes. I would like to suggest that people address those questions directly to you. Do you have any suggestion, like going on Twitter and mention you, or do you prefer by mail? Please. What's your suggestion?
Please, I'm happy. Like, feel free to ask those questions on Twitter. I think my front slide. Let me see how we can share my. Let me share my screen again for a second.
Okay.
This is okay. This is my Twitter contact, so feel free to ping me there. And what I would like to suggest is that we take these questions and do a follow-up for this once we publish the recording, and take some of these questions and answer them offline. And I'm going to do the due diligence to answer everyone online, because we're at the end of the talk.
Perfect. So once more, thank you so much, Marius, for this great presentation, and also thank you for all the people that were here live and that are watching this record. And please sign up to developers.redhat.com so you can be aware of our next DevNation Live events. Thank you so much, and have a nice day.